Let's see here. Let's see here. Let's see here. All right, we're good. Okie dokie, I think we are good. Okay. In this stream, I want to do a couple things. Most important, show you how I go about transforming models and equations into code from engineering papers or whatever. So, yeah, let's get started. I am going to pull up Sea Lion. Let's make sure that's good. Yep, okay, cool. All right, so let's see here what we got. We already have a module called console module. So I think to demonstrate this, let's create a new one, and we're going to call it bus module, I guess, because I already wanted to do some kind of output bus thing, kind of like the Slate console collection thing. So I'm going to call it master bus. We could do some cool stuff in here, like do the the saturation, whatever, and also do some other console stuff like crosstalk, stuff like that. Rogma once. And let's go into the process block and include that. Master bus. All right, and let's see. We're basically going to copy this. Yeah, I'm just going to copy this. I don't really think we need this base module thing, but I'm going to leave it in there. All right, we'll take that out. And we'll take console module. And we'll call it master bus. That should all be good. Process block. Set drive. Okay. We probably don't need this 2pi. Cool. Okay. I guess I will also get rid of... Yeah, let's just get rid of that distortion here. And we're going to say... Let's see. Class master bus. Redefinition of master bus. How did I manage that? Oh, what did I do? I somehow... Okay. Oh, yeah, I did replace, and it did all instances of that console module. So that should be good. And that should be fixed now. Yep, okay. Process block. Let's go and make... Oh, this is console module. So let's make a master bus one. And we'll call it master bus. And we'll do all the same prepare stuff. And we will call process. Now by default, we should get no change, right? We're just passing the input to the output. So let's do that real quick and make sure it works. Okie dokie, plugins, components, okay. Projects, plugins, me, comment channel strip, debug, artifacts. What's up, Joshua Joseph? Let's pull that up in the old plugin doctor. Comment channel. Okay. And nothing happens? Okay, good. Just like we expected. All right, so let me show you what we're working with. You may be familiar with this. So this is an addendum to Will Perkle's designing, what's it called? Designing audio effect plugins in C++. Will Perkle. And he released this addendum that's all about distortion and amps and tubes and all that stuff. So he shows us there's a bunch of models that he basically built from patents that are at the end of the addendum. And one in particular that I always thought was cool was this Paletti one. And this is the block diagram for it. And it kind of shows you what the output's supposed to look like. It's pretty tube ampy. It's cool. Definitely different from the algorithm we have now that uses that circle map. And this isn't too difficult. All you really have to do is follow the signal chain. And I guess one thing that isn't super obvious is that this pathway right here is the positive side of the signal, and then this pathway is the negative side. So that's the only thing. And it uses 4 wave shapers. So 2 of them are asymmetrical, and it uses 2 symmetrical ones. And then you've got some DC offset filters here. And yeah, it shows us what the wave shaper is. This is the equation for it. So you can see that the negative side of the signal passes through this, and then the positive side passes through this. And what makes it symmetrical or asymmetrical, if you read, is the values you use for these limit values. So like limit negative and limit positive. And if I remember correctly, actually, let me just look. I forgot. I'm pretty sure they are symmetrical when they have the same values. The symmetrical version has ln equal lp. Yes, okay. So just want to make sure. Now, we can do this a bunch of different ways. I'm going to do it the very straightforward, naive kind of way. I'm just going to have an if statement that says if negative, do this, else do this. And then after we implement this, I'll show you a way to eliminate the if branches. And that'll speed up your code quite a bit, because if statements in the audio sample loop, I guess they're not quite as bad in the process block, but if you do it sample by sample, it's much worse, because if you do something that is saying if positive do this, else negative do this. So the CPU is going to try to guess which path the next call is going to take. And since audio is it's unable, the CPU is unable to accurately guess because the samples are coming in either negative or positive from the input, and it has no idea what's coming through. So it's going to be wrong at least half the time. So if you can eliminate if branches, conditional branches, you are going to speed up the sample loop quite a bit. So yeah, but let's do this first. We are going to create a function, and we're going to call this, I guess, just wave shaper. It'll be a static inline float, and we'll call it get wave shaped. So it's going to take in an input, obviously. So let's do a float, call it xn. And we are going to do this. Okay. At the very least, to test just that part, we are going to say get wave shaped and pass it xn. Okie dokie. That should be good. And then what we're going to do is in this method, we're not going to worry about the block diagram yet because we're not going to worry about this because we need just the wave shaper so that we can place it. So we're doing the wave shaper first. So let's do that. All right, here we are. All right, so let's say, what's the best way to do this? I guess we'll say float yn equals 0, whatever. We'll use that in the future. And at the most basic level, let's do our if statement. So we'll say if xn greater than or equal to 0, we do something, else we do something else. Cool. Okay. So keep switching back and forth so we can see. Let's do the positive one. We also need k, and we need our 2 limit values. So let's do that. Const float k, const float limit negative, const float limit positive. Cool. Okay. So here we go in the positive one. So it's k times xn. Let's see. Yeah, let's make it really clear. I'm going to do this. Const float numerator is equal to xn times k. Const float denominator is equal to what? 1 minus, we got k times xn again. And I'm not actually going to use the variable numerator right here because I think that would probably get a little confusing. So I'm going to do that divided by ln. Cool. Let's see, that's fine. Order of operations times, yep, okay, that should be good. All right. And now we'll just say yn is equal to numerator divided by denominator. Cool. Numerator, which is this, denominator, which is, oh, I did the wrong one. This is supposed to be the positive one. So plus and LP. All right. Move on to the negative, which is simple. So what I just had, that's going to be 1 minus that, and then that's going to be ln. Okay, cool. And then return yn. That should be good. Okie dokie. Let's do this with, let's just make sure it worked. So for K, LN, and LP, I'm just going to go to the paper and just put in some of the values he had as an example. So 6.6 and 0.6. Okay. So let's do, and they have a K. 40. Okay. That seems like a lot, but let's do it. Let's do 6.6 and 0.6. Yeah, we do have the K variable right here, but I'm just going to put it in here just kind of statically so that we could just make sure that this works and doesn't blow up or something. All right, let's see how that goes. Okay. That was quick. Awesome. And what I really like about Plugin Doctor is if that DSP blows up, we don't have to hear it. Okay, cool. Looks like it's working. There's definitely a DC offset, but it's working. Cool. The shape is correct. All right. For the most part. Okay, that's good. That 40 might be too ridiculous, but we'll see. In fact, let's just go ahead and, yeah, let's just go ahead and do it. So we got drive. So this one is not going to be 0 to 1. It's going to be a regular drive, which would be from like 0 to 10 or 0 to 20 or whatever. So this one we do need decibels to gain. And then value. And then instead of 40, we'll pass in this K, which is our drive. And we need to go into the process block and right here do the same thing. Do master bus, set drive. If I remember correctly, that's from 0 to 10. So I guess we'll just leave it the way it is and we should be good. Okay. Also, feel free to stop me and ask for an explanation if I do something too quick. Oh, it did a build and I missed it? Yeah, okay, good. Here it is, okay. All right, there we go. Looks like it's gonna work. Let's see. Yeah, okay. That drives it, that's cool, okay. We can obviously add more gain, but that's good for now. We have our basic algorithm. So we've got the wave shaper, which will correspond to these 4 blocks. And we basically just need to change the values in these that we pass in, the LN and the LP, for each of these blocks. So this is a positive, this is the asymmetrical one. This is the asymmetrical one, so they need to be not the same value, and then we'll do the same values for the symmetrical ones. And we also need these high pass filters, which is simple. I'll just use some Linkwitz-Riley filters for that. So I'll do an array of juice DSP Linkwitz-Riley filters. Oh, sorry. Float. remember we have 2 of them. So these are going to be DC filters. For auto filter and DC filters, we need to prepare it. Yep, with spec, and then we need to also filter set type, which is going to be high pass. What is it? High pass. And then lastly, we will set the cutoff. 20 hertz should be good. Okay. And we're going to use that whenever we set up these. So kind of the same thing. We're going to set up an if statement to divide these sections into the 2 polarities, negative and positive. So I think what we'll do is, I guess we'll just make another. Yeah, we'll just make another. Or we could just build the whole thing. I wonder what would look easier. It'd probably be easier if we just do another free function. So let's do this, and we'll say get Paletti, since that's what it's called in the paper. I guess we'll do kind of the same thing. Let's grab this. Actually, we'll grab this whole thing, because all we need to change is the stuff inside. And we need to pass X in yeah, I think that's all we're going to pass. Yes. Okay, let's just see how it goes. Okay, so the positive section, if we look at the paper, the first thing is a asymmetrical wave shaper. So we can take what we did here. Yes, get wave shaped. I guess let's also pass K. Okay, so we'll say yn is equal to get wave shaped this asymmetrical one. Okay, pretty simple. That takes care of this block right here. We're also, oh, you know what? Since we have those filters, we need to also take in the channel. So this would be yn equal to m DC filters. And we're going to use the one for the channel. It doesn't like something. What did I do? DC filters. What? Oh, because it's a static function. Okay. Process sample channel. And yn. Okay. So we've done this block, and now we have to do a symmetrical one. So we'll just take the same thing here. And I don't remember if I doubled up 6.6 or if I did 0.6. I'm going to go with 0.6. Okay, and make sure we're actually taking in that. Okay, so that should be our entire section. Okay, one thing that I just realized is we actually need two of these. We need yn positive and we need yn negative because we need to add them together at the end. Okay, so we need to do all this for positive. So yn positive equals that, that, and that. Okay, so now our entire positive side is done. Yes? Cool. Okay. So we just need to do the same thing for the negative. We can really just copy and paste this. And we'll do this with negative. Yes. Yep. Also, I don't remember if I, between the two sides, swapped the values. We're just going to have to see what it looks like. So let's just add positive and negative back together. And we need to call Git Paletti. So xn k and our channel. Okay, I think that's it. Good. Okay. Well, let's just see what happens. Okay, it's done. Plugin doctor. Let's see here. Oh, that doesn't look great. Well, actually, that might be okay. Let's see. Huh, okay. It's doing something. There's no DC offset, which is good. Okay, let's see. Yeah, it's not quite right. Because it should look like this. So let's see. It could be a bunch of things. Okay, so okay, so maybe this is what it is. The positive uses 6.6 and 0.6. Okay. Let me close plugin doctor. So the positive, which was this one, it uses, what order is it again? LN and LP. LP and LN. Okay. So LP needs to be 6.6, which is the last one. So, okay. 6.6. Now, does that mean both of them need to be the same? Because the other option is for, oh wait, hold on. So the first one, oh, 6, okay, and then this one, they need to be the same values because they need to be symmetrical. So that one, correct, reversed, and then I don't know, this one also 6.6 for both of them. I don't know if it matters. I do have an implementation that is correct and works. So if we can't get it, I'll just look and see what I did on that one. Zoe, can you stop? Okay, that looks better. Oh, this might be correct. Well, I think maybe we need to change the symmetrical ones might need to be the 0.6 ones. That looks strange. Okay. Okay, that might be close to correct. So let me add more gain. So this is 0 to 10. So let's do, I don't know. Let's make it 0 to 100. I mean, we'll actually go that high, but, you know, we'll be able to see. Zoe, stop. Did I press build? I did. Comment channel, okay. Not quite. Okay, so the other option we have says it really doesn't say, right? It doesn't say if both symmetrical ones use the same values. So okay. Let's just go back real quick. Let's give these 6.6 again, since now we have more. Well, actually, yeah, let's do this. Let's give the first one 6.6s and then the second one 0.6s, and then we can switch those around if they don't look correct. What we got here? Oh, we got some DC offset. That's kind of weird. Yeah, that's definitely not correct. Let's see. I wonder. I'm going to take a little peek at. Do I have that project open? Let's see. Open. This one? Yeah. Let's see. Take a quick peek because I'm stupid. So, oh, it looks like I had to change values. Interesting, for it to work correctly. Yeah, because I used some 1.6s here. I wonder how I came to that conclusion. Probably just a bunch of trial and error. So, okay. So our positive asymmetrical one is probably correct. Now, The positive not asymmetrical apparently is 1.6. Okay. And then the negative not symmetrical is the opposite. So that is true. And then, okay, apparently. All right. 1.6. Okay. Let's see if we get the same result. That looks more correct, actually. Still not quite the same. Let me grab this right here. Zoom the screen. Which screen? Just plug-in doctor or? Or do you mean the code? Zoom on the code. I can make the code bigger. So, hold on, let me see. LNLP. LN. Oh, actually, I don't know what the inputs are for that one. Oh, well. I don't really know why it's not quite perfect. YN positive, YN positive. YN positive, YN positive, YN positive. Negative, 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 negative. I don't think it actually works in C-line that way. If I do command plus, it doesn't do anything, so I have to... Is this... Okay, so is this big enough right now? After I had increased it by 25%? There's a delay on the chat, so I gotta see here for a second. Yeah, okay, cool. All right, so I don't see anything obviously wrong with this. It's not quite... I am taking this paper, which is an addendum to Will Perkle's Designing Audio Effects Plugins, and I am going from the equations and the block diagram and just transforming it into code. So maybe I'll try one more thing, because the shape just isn't perfect. It's very close. I could reverse these. I doubt it really makes a difference, but I'll give it a shot. Nope, that's farther away. That's okay. It's pretty close. So, we just look one more time. Anything weird happen? Oh, I wonder if... So he says in the paper that you can use the output from just up to this point, and you could use the output at the end. I don't think you're supposed to add them together. That would be the only other thing. Okay. Oh well. Let's see what happens when we try to transform this to the mask. Okay. So to get rid of the if statements, we need to do this pattern that is called a mask, where you just have two variables. One is the positive signal, one is the negative, without having to switch between them. So we could do this a couple ways. We could, and I'm going to try to do it a different way from... I've got a project where it's implemented correctly here, and I'm going to try to do it... Oh, actually, that is the same way I was going to do it, so... Oh, well. So we need a variable to hold our masked signal. So we're going to do const float, call it AX, is equal to the absolute value of xn, correct? Yes. Okay. Then what we could do is just a little math trick to get our signal. So we'll say not const, probably just do regular float. What should I call it? I guess xn. Yeah, do the same thing. Xn negative and xn x or yn is fine. Yeah, it's fine. Positive. So a little trick we'll do is 0.5 times. This is positive, so it'll be ax plus an. Oh, I'm sorry, not an, xn. And then we'll get rid of that. We'll do the same thing for negative. And this is going to be ax minus xn, correct? Or xn minus ax. It probably doesn't matter, but I'm going to do it like that. Okay. So obviously, subtract something from itself, it's going to get negative. So we have the absolute value right here. So this is always, the xn is all, or the ax is always going to be positive. So negative and positive, and then we have the 0.5 because adding these together is essentially doing the same thing as like xn times 2, right? If you add two things that are the same together, it'll be double the size. And now we can get rid of this, and we could just say the same thing, basically. Also, if you're using CLine, or if you see me use a key command that you don't know what it was, feel free to stop me. If you do Option Command L and C line, it will format all the code. Okay, so what we got to do here is positive and negative. Something I definitely love about C line is it showed me that I wasn't actually using Y in positive or Y in negative. So it kind of reminded me to actually do it. Okay, cool. All right, so let's just build that and make sure it works. And as I'm looking at this, the order is a little different from what I've implemented before, which kind of doesn't make sense to me right now. But that's the thing about code, right? You do something 2 days ago and you look at it and it doesn't make sense. Past you knew what you were doing. Past you did all the research and the testing. And there's probably a reason. And what did past you do? Not write it down. Cool. Let's do that real quick. Make sure we get the same result. Comment. Yes. Okay. Yep, that looks correct. There is a low end bump. It's not that big on actual musical material though. It's looks worse than it is. Oh wait, are we getting it? Yeah, I think that's correct. Pretty much. It is a little funny looking. If we take a look at this, I did the positive and negative asymmetrical one. Then I did the filter. Then I did the... Which, isn't this the same thing? Like if I do... Like this would be the two asymmetrical ones. So this line right here would be this. And the second line, this one, would be this. Then we do our two filters. And then we do the second blocks, these two. But isn't this the same as what just happened? Or how it was just a minute ago? Let's build. Let's see. Yeah, it's the same. The shape is very close. It's got the correct hard top, and then it kind of has that section in the middle that flattens out, but it's doing it for it's way too accentuated. So I wonder if I reversed my values here. So the positive asymmetrical one, let's just look at the paper one more time. The positive input, LP is 6.6. Which one is LP? The last one. Yeah, 6.6 and 0.6. And then the other one should be opposite. Now in this one that I implemented earlier, let me go here real quick. This is it right here. LN LP. LN LP. Okay, so that's not reversed. Maybe I messed up the wave shaper. Now we can do the same thing for the wave shaper that we did here with the mask. So yeah, let's do that. So we'll basically just take this. Can we do the same exact way? Let me see. I think so. All right, let's do it. So we've got this. Okay. It's not gonna be exactly the same, but let's see. So numerator definitely is the same for both, right? If we go up to this equation here, the numerator is k times xn, so that's the same. The only difference is using LP for positive. Oh, this is why. Oh, wait. No, LP, LN. That's correct. Positive 1 plus, negative 1 minus. Okay, so yeah. That should be fine. What we could do is we could also do float denominator negative, which is equal to this. And then we can have denominator positive. Which is that, and that's this one. And I don't like putting negative on top of positive for some reason. We're going to do positive first. Okay. So also we need to do this, right? Oh. And then negative here. Good. Okay. And then what do? We need to what do we need to do? We're basically going to do this. We're going to say yn, basically, this is kind of like a little skeleton, is equal to numerator, or what's it called? Oh, I didn't make one. Let me do that. Const float numerator. Oh, actually, does it matter? Let's do the same thing. Numerator positive is equal to yn positive times k. And then the same thing for negative. Let's see, negative. And we say negative. And then basically yn is going to be whichever one we need, which is negative or positive. So how do we do that intelligently? Because I am kind of doing it blind, a different way than I did the first time, because I wanted to not just copy and paste. So we could just do, this is what we're going to do. We're going to do yn positive is equal to the numerator positive divided by denominator positive. And then we're going to do negative equal to numerator negative divided by denominator negative. And then we're just going to return y positive plus y negative. And I guess we don't need this y in. Cool. So now instead of if branches, we have just math. So we've got addition, subtraction, and multiplication here, which is, that's nothing. That's nothing for the CPU to handle. And we've got multiplication right here, multiplication of, these are not massive numbers, so that's also pretty much nothing. The only thing that we have that's somewhat CPU intensive is these divides. But I mean, on a modern CPU, is that even going to be a problem? It's probably just going to optimize away the, well, maybe not, because it is based on the input, so maybe not. But I mean, still, it's not a big deal. So let me just make sure we've got, I just want to check the equation real quick. Our numerator is definitely correct, right? Okay, so then it's numerator divided by n, right? Denominator positive is, or I'm sorry, denominator negative is 1 minus yn negative. Oh, I think I just made a huge mistake. 1 minus yn. Yes, if you go on the last video that I uploaded, like the 20-minute one or whatever, the one, I don't even remember what it was called. That was the one that I did. It was the distortion one. So yeah, that one should have the Discord corrected. Oh wait, no, this is correct. Yn negative times k divided by ln. Right? Negative. Okay, so that should be correct. I didn't make a mistake. Let's build that and see if we get the same result. Comment. Okay, so yeah, it looks like it's still fine. Okay. So let's see. Halfway would be 50. So that's like 25. So maybe like 20 is what we actually need. Let me check some different frequencies. Let's go to 1,000 and see what it looks like. Let me zoom in. Okay. Let's see. It's pretty close. It's similar at least. Let me go reduce the amount of gain we get to something more reasonable. So what did I say? A quarter of this. So I don't know. Maybe we'll say 3. 0 to 30 is probably fine. And then let me take a look one more time at the other project I had. This is my, so this equation right here that we've implemented in this other project is this. I went about it a different way, but this is all the same. Actually, it's not. That's interesting. Okay, so here we go. We're going to go into a new topic. This is going to be called responsible chat GPT usage. I'm going to get my boy pulled up. And here's the thing. Chat GPT can be really helpful or it can be really not helpful. And the trick is you can't just tell it, write me a distortion that models this equation and amp and signal flow. You have to be very specific. So you have to do all the legwork of implementing the general architecture or general idea of your question. And you need to get it to a point where it's just a very minute detail for ChatGPT. Because once it has to write more than 10 or 15 lines, it's going to start making stuff up and not make any sense. So I'm going to give it this. Which project is this? Right. Okay. So I'm going to go to this paper. I'm going to take a quick screenshot here. Give it that. And I'm going to say, this is my implementation of the attached image. Is it correct? Don't just try to make me happy. Actually tell me if it's correct or not, because these models are trained to kind of just parrot back your to kind of like uplift you, and you can literally tell it something you know is incorrect and be like, is this correct? And it'll be like, yes, good job. And you'll be like, no, it's not correct. And it'll say, oh yeah, actually it's not correct. So you have to explicitly tell it that you want the actual correct answer. And I'll give it my code. And let's see what happens. Also, if you download the actual app and don't use it in the browser, the thinking time is reduced, it seems. So halfway. Yep, good. Then yes. Okay, so you compute. And then make sure that it actually gives this back to you correctly. So yeah, this is the positive one with LP. That's the negative one. Okay. Only because if someone later changed the half-wave logic, you'd want to be careful. A more explicit and safer expression would be denominator negative equals 1 minus. Okay. So it's saying denominator negative 1 minus yn negative. Yeah, it's saying I don't know if that's actually, I don't think that's a problem. So it says it's correct. Let's listen to it, because if it wasn't correct, I think we would hear some little artifacts. And then also we'll see that I think we need to increase the volume, because it looks like it's coming out about half volume. Not quite half, a little bit less. But whenever we increase the gain, let's see, let me zoom in right here. Is this still too much gain? Yeah, it is. Like way too much. Okay. Wait. Let me just make sure. Okay, this is 0 to 10. All right, so we should be good with 0 to 10. So let's do that. And then let's actually listen to it. And I set up Logic to actually go through OBS before so that it doesn't shut down on me again. So we should be good on that. Let me just pop this in here and give it one more check. Yeah, I think that's going to be good. It still goes a little bit above, but I think that's fine for now. Let me try lower frequency just to see. Okay. That is somewhat similar, I guess. One more thing we could do, I guess, is I could give it this, and I could say, this is another implementation I did. Is it different? It's mathematically equivalent to first implement, only written in a different algebraic branchless form. Yeah. I figured that would be the case. Oh well, let's listen to it. Let's see what happens. Let's see, I got this right here. That shouldn't be too loud. Should be a little lower than my voice, I think. So I'll also listen to it myself here. And let's bring it in. Viator, Comet, Strip, okay. Yep, sounds like distortion. I hope that's not destroying your ears. Okay, so that's drums. We could, I don't really have all the loops downloaded, like the Apple ones. So if I get like a guitar and I do like basically nut alt pop, yeah, sure. Let's alt pop acoustic. Let's see, how's that look for y'all? That should be audible. That does sound pretty accurate for what the input of an amp is kind of listening for. So I think that's good. It sounds a little like a fuzz on this acoustic, but that could just be because it's acoustic. I could see if I could find an electric, like a clean electric. I don't know if there's anything. Blues guitar might work. It's already distorted, but let's just give it a try. Okay. It's something. It definitely sounds like amplifier distortion, I think. I mean, I think it's cool. And it, what I kind of wanted to do was use this for this master oh, wrong one. For this master bus module. And I think that's that's way too much distortion. So, one more thing we could do is we could add in, we can make it more subtle by adding in a mix. So like, We know K is from 0 to 20 or 0 to 10. So we could do this. So we can make a float mix is equal to that, which should put it at between 0 and 1 instead of 0 and 10. Now, we're not going to leave it like this because if we change the parameter or the scaling outside of this, it's going to break. But this is good for now. We could say const float yn is equal to this. And then we'll do our mix logic. So to mix, you do 1 minus your mix, and that is going to be multiplied by your dry input. And then you're going to add your actual wet input times mix. So when mix is 1, that means 1 minus 1 equals 0. So your dry is going to be all the way silent, and then the opposite. So, that should make it more subtle and less of a volume. I think less of a volume difference. Let's see. Let's see what it looks like in Plugin Doctor. Channel, okay. Okay. I actually kind of like this whenever you have your mix down to 0 and there's still a tiny bit of, we've got this bump down here at like 50 hertz, and then we got a little bit of a ramp up to maybe 200. That's kind of cool because it kind of models hardware. How the thing being on still has a tone of its own. All right, so here we go. Dry. Let's mix it here. Cool, that is very subtle. Is it just me, or at the end here, was it supposed to be more distorted than this? Let's go listen to it. And let's listen to it on the drums, because it's at least a kind of thick signal, and we can see what it sounds like here. Okay, so it's the same. We're getting the same sound at the top end, but we're not getting as much of a volume dip since the mix is 0. Yeah, we've got a very smooth gain increase because of the mix, which I think is actually really good and kind of models what would happen if this was like that silver slate console thing. So like right here at 5, halfway, I still hear some distortion, but it's subtle and it still sounds great. And we got a bit of a volume boost, and we're also probably getting a bit of compression. Let's look at the meter. Probably not as much. Yeah, I mean, a little bit. Yeah, we get a bit of a kind of pushed into a compressor behavior. Pretty subtle. Okay. Cool. Well, there you go. We turned that paper, the equations and the signal chain, into code. And it works. It sounds like distortion. So yeah. I think that's going to do it for this one. I'm going to leave it this way. Or actually, let's do this before we go. Let's think about this mix part. How can we make this not break? Because if we go into the processor and we change this amount from 10 to something else, we are going to have a problem. Well, I mean, I guess you could say that about anything. So, okay. Yeah, okay, so what we could do, a very simple thing we could do, is we can just limit K, J limit. So the lower limit's going to be 0, and the upper limit's going to be 10. And then the value that we're limiting is K. So even if we go change it to 100, whenever we pass at 100, it'll only go up to 10. So it's not the most perfect solution, but it does at least clip it to a desired range. So that's the very least we could do. Okay. We could leave it like that. Maybe, let's see. Maybe next time we could do some crosstalk in the master bus. What do y'all think? Do y'all have any questions or anything about anything I did? There's a bit of a delay between chat and me. So I'm not sure how long I should wait until I assume that nobody has any questions or anything. How did you incorporate what you read in the code? So, reading the equations was easy, or I should say, yeah. So this is the wave shaper that is used for these 4 blocks right here. Now, the equation, transforming the equation into code is easy because you're almost doing the exact same thing that's written. So what we did was, and here's the other thing, is that you see we have one kind of block for the negative signal, so xn less than 0, and then one block for the positive. And instead of using an if statement to separate the positive and negative, we use this mask pattern. So we have a positive version of the signal. We create 2 variables, yn positive and yn negative. So yn positive is going to be that always positive signal plus the input, and then times 5, because the input plus the absolute version of it is going to be basically 2 times as loud. And then for the negative one, we're saying our input minus that absolute value, which is always going to be negative. So numerator positive is just a handy way to look at this, the actual numerator, so k times xn. And it's the same thing for both of them. So we got numerator positive and negative, using yn positive and yn negative times k. Then we have the denominator for each one. So the positive one is 1 plus yn positive times k, which is this, k times yn positive. And then that is divided by the LP, which we are passing here. And then the same thing for the negative, 1 minus yn negative times k divided by the ln, which is the limit negative. And then once we have those things, we can perform the operation. So when we know our positive signal is going to be the positive numerator divided by the denominator that's positive, and then vice versa for the negative. And we just add them together. And that gives us this equation right here. And then the paper tells us that that wave shaper is used in these 4 blocks. Now, it says asymmetrical and symmetrical. The paper told us that the wave shaper is asymmetrical when Ln and Lp are not equal to each other. So it's symmetrical when they are. So this first one, right here, we implemented it. So we have our first positive asymmetrical one, right? So this one, positive asymmetrical. So our Ln and Lp don't match, so they're going to be asymmetrical. And same thing for the negative right here. So this line is this block, and this line is this block. And then we do our high pass filters in between, and then we do the symmetrical ones. And the paper suggested that the positive input should use LP is 6.6, LN is 0.6, and then the negative one, LP equals 0.6, LN equals 6.6, which we did right here. And it didn't suggest any values for the symmetrical one. So I input these. This is something that I had tried before. I think I had did a bunch of testing and found that these values were good. In fact, we can let's change that and let's see const float. I'm just gonna call it a I can't spell symmetrical. 2 M's, I think. Nope, sorry, symmetrical is equal to, we'll do a juice live constant, and we have 1.6 by default. So let's do that. Symmetrical, and then we'll just pass this here. Yes, okay, and that should be good enough to test. Having this in the sample loop is not the best thing, but we're just testing. Obviously, we wouldn't release a debug build anyway, and that juice live constant only works in debug. Let's open her up and see what happened. Channel, yes. Okay, we've got our juice live constant. So let me turn the gain all the way up, and we will look at our waveform. Oh, I forgot. It's it might be too subtle to check. So let's see what happens when we change these. That doesn't really make a difference. Actually, if anything, I think a lower value, we get more of that little fold in the middle that we see in the paper, because it suggests that it should look more like this. And you know what? It used a K value. Wait. So it's testing at 150 hertz. So let's go ahead and we'll leave that the way it is. What did I want to do? I wanted to give it a specific K. Okay. Mix. That's fine. Okay, so let's give it. It suggested 25. Let's see what happens. Should be good. Okay. Let's see. Yo, Unk. Oh, that looks very distorted. Let's see. What we got here? That's pretty crazy looking. Let's see. All it's really changing. How did I get this 1.6 figure? Oh, also let me try 150. That certainly didn't help. Okay. I think something is wrong. I'm going to get rid of this mix part. I'm also going to change these to 10. Let's see. Const float gain equal to 10.0. I guess I'll just do a constant here too. Because I see something in the waveform that's kind of telling. Unless I'm just mistaken. Okay, what we got here? See, that's more... This is just too wide, though. Imagine the tops are cut off at -1 and 1. That's kind of what we want, but this is way too much. Let's see. Okay. This doesn't look right. So the left side of the waveform is different from the right side here. And to me, that would mean that something is backwards with our negative and positive. Yeah, you see, if you follow the left side all the way up and then all the way down, it's definitely different. Let's just look over the code one more time and make sure. Let me also look at that other project real quick. So I got the master bus. Did I do anything, any kind of multiplier or anything? Nope. Just positive plus negative. Okay. Where's K? Oh, I also set K to some kind of static variable. Probably just in making it more subtle. That shouldn't make a difference to the actual wave shape. Okay. All right, so we've got AX. So positive is AX plus input, and then negative is input minus AX, which is correct. Okay. Positive. Okay. Negative. 0.6 and 6, and then 6.6 and 0.6. Yep. Okay. Positive, negative. Positive, positive, negative, negative, positive, negative. Okay, so that seems correct. What about this one? Positive plus, negative minus. Okay. Numerator positive, positive, numerator negative, negative. Denominator positive, 1 plus. LP, which is positive, negative, 1 minus the negative times K, and then Ln, which is negative. Positive, 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 negative, negative, negative. I mean, it sure looks correct in the code, and it sure sounds correct in logic. But I guess what we could do to really see, I'm just going to copy this code over real quick and see if it makes a difference. And I need, sure, I'll just call it the same things. Do you have any book recommendations? Yeah, so Designing Audio Effect Plugins in C++ by Will Perkle. Hack Audio by I don't remember. Hack Audio. Eric Tarr, sorry, yeah. This is great. This is a really beginner book, and he goes through every basic effect. So like distortion, compression, filters, tremolo, stuff like that. And it's a very simple to follow example. He uses code, but he uses MATLAB code, which isn't, it's all simple and small examples. So you should be able to understand how it could relate to C++. That's probably the best beginner book. Grab this real quick. Let's do that. And then this clamp away from 0, I guess, could be the thing that's our bottleneck in making it not perfect. I don't even remember why. Like, I don't even remember what the point of this is. Yeah, okay, so it's a hard clipper. It's a hard clipper, and we've got this epsilon, which is just a very, very small number, and we're adding it to 0 so that we never divide by 0. I don't know if it's even really necessary, but let's go ahead and put it in here. Yeah, so we've got this tiny number. We're doing the max of our value input, which is I don't even remember how this works. What's wrong with this? Oh, we need to make it static. Of course. Static. All right. Okay, so all we did was change that. Let's let that build and see if that changes anything. It doesn't seem like it. No, it's the same. Okay, so maybe I was wrong. Maybe that other one also was not perfect. Okay. Well, I don't know. It's super close. The thing is that when Will Perkle implemented this, he used values from the patent that he was looking at whenever he made this, and I've seen other people make comments about how they also saw that his values worked in hardware, but not in software. So like on a hardware oscilloscope, the values he used translated perfectly. And when they did software implementations, it also did not transfer absolutely perfectly. So I don't know. Sometimes it just be like that. The only other option, I definitely didn't add the two different types of outputs together, right? Let's see. No, I didn't do that. It's the same thing. Okay, well, all right. There you go. I hope my explanation of going from the paper to the code was good enough and you were able to understand it. Um, I think maybe next time we'll put this mix stuff back in because we do want this effect to be subtle. So we'll leave it all like that. Okay, and then we're good. All right. And then the other thing we might implement is crosstalk, which is something that happened in a lot of analog consoles where the left channel could spill into the right channel a bit, or the right channel spill into the left channel. And that will give you definitely a different vibe. Anything that you can do that makes it feel more real. Also, another trick is to put in some white noise, really, really subtle in there, like at negative 70 dB, could actually make a decent difference. Also, having some random noise in your DSP will make it so that if you have a track in Logic and you put your plug in and you bounce it out and then you bounce it out again, you take those two bounces, you flip the phase of one and add them together, they're not going to cancel out. They're going to almost cancel out. There's just going to be you're going to hear the signal just very small little blips and bloops of it, and that's because of the random values being different. So that's a neat trick. Which, people who use your plugins always want to do stuff like null tests and all that stuff. So if you keep them guessing, they're going to think it's really fancy. So yeah, thanks for watching. I hope that was somewhat enjoyable, and this will also be edited down into a much cleaner and quicker video. So if you want to reference it again, there will definitely be a shorter video for it. So yeah, cool. Thanks for watching. I hope you enjoyed it. I'll be back on Wednesday night. All right. See ya.